Hello friends, myself Dr. Nandakumar Rawale from College of Engineering Ambazogai is going to deal with fluid mechanics. So in previous class we have discussed about power transmission through pipe, condition for maximum transmission of power and maximum efficiency of transmission of power through the pipe. So today we are going to discuss about water hammer in the pipes. So what this water hammer is, water hammer in the pipes is that we see. Let us assume that there is one tank having some liquid stored in it to the height h above the center of this pipe, and the pipe is connected to the tank. So when there is a wall which is opened, so say for example this is the wall and in open condition, so this wall is in open condition, at that time the liquid starts to flow through this pipe at velocity v through the pipe of diameter d and cross-sectional area A. The length of pipe is assumed to be L. So what happens when this liquid is coming out of this pipe with a velocity v? So there is no hammering action over this pipe. But if we close this wall, suddenly the momentum of this water or liquid flowing through this pipe is suddenly stopped, and that creates the shock. So here the momentum of flowing water will be destroyed, and consequently a wave of high pressure will be developed, and this high pressure will be transmitted along the pipe in the reverse direction, and this pressure which is transmitted is at the velocity equal to the velocity of sound wave and may create noise called knocking. And this process of knocking or hammering action which is developed because of sudden closing of this wall is known as a water hammer. So this is simply when we destroy the kinetic energy, so that kinetic energy gets converted into the hammering action, and that we say as a water hammer. So this water hammering process is going to get created because of four reasons. The very first reason is velocity of this water. So it is directly proportional to the velocity of water. If the velocity is very high, then the hammering action will be very high. And the time taken to close this wall is also one of the important parameter. If we close this wall suddenly, then this velocity which is at v meters per second is suddenly brought to 0 meters per second. So momentum is stopped within no time from velocity v to 0 meters per second, and that is one of the reason because of which this water hammering action is developed. Then next one is we can say that elastic properties of this pipe. So if this pipe is rigid, then the shock developed within this pipe will not be absorbed anywhere. If this pipe is flexible, then this pipe will expand to absorb the shock, or it will elongate with the water hammering action, and that reduces the intensity of water hammering. But if the pipe is rigid, then the water hammering is not going, intensity of water hammering is not going to get reduced. And third one is the length of pipe. Fourth one is the length of pipe. So larger is the length of pipe, larger will be the weight of liquid flowing through this pipe, and larger is the weight of fluid flowing through this pipe, larger will be the water hammering action. So this is what about the water hammering. Now we can see here the pressure rise due to the water hammer depends on four parameters. As told you, the velocity of water flowing through the pipe, if it is higher, the velocity higher will be the water hammering intensity. And the length of pipe is also responsible. As I told you, the weight of water present in the longer pipe is more than the pipe of shorter length, therefore the water hammering action will be larger. Time taken to close this wall. So if we are going to close this wall in very short time, then water hammering action will be at larger intensity. And if the wall is closed gradually, that is nothing but we are going to stop this velocity step by step, then the water hammering action may not be so intense. Or if the material of pipe is elastic material, then the water hammering or shocks will be absorbed by this pipe material, and the intensity of water hammering gets reduced. So now there are three kinds of water hammering actions that are registered here. So very first is when we close this wall gradually. When we close wall gradually, the water hammering action will be not so intense. And second one is if we close wall suddenly, considering the pipe to be rigid. So if the pipe is rigid, then the water hammering action will be very high, or noise created or knocking created will be very high when we close the wall suddenly and the pipe is rigid. But if the pipe is flexible, the intensity of water hammering will be not so intense as compared with the rigid pipe. Now we will see first case one by one. So in very first case, what we are assuming is gradual closure of wall. So if wall is closed gradually, the intensity of water hammering will be very smooth, and that will not be even sensed. So let us assume that the water is flowing through the pipe as we have shown in the previous figure. Wall is provided at the end of this pipe, and the pipe is having area A and length L. So let L be the length of pipe and D be the diameter of pipe. H is the head of water available at the inlet of pipe, that is in the tank, and V is the velocity of flow in the pipe, and A is the cross sectional area of pipe, whereas P is the pressure intensity and T is the time required for wall to close in seconds. So intensity of wave produced. So P is the intensity of wave produced. Now let us assume that mass of water present in a pipe, mass of water in pipe is mass density into volume of water. So if volume of water is taken as area into length of pipe, so if we know cross sectional area and length of pipe, then we can find out volume. So rho A is the cross sectional area and L is the length of pipe, and this wall is closed gradually in time t seconds. So if we are taking time t seconds to close, time taken to close the wall. So what happens here? The retardation process takes place. What is the retardation? The velocity, which is velocity of water, is v meters per second, and we are going to convert this velocity to 0 meters per second by closing this wall. So the reduction in the velocity from v meters per second to 0 meters per second within a time t, so that is known as the process of retardation. So retardation of water, we assume that retardation of water is equal to change in velocity divided by time taken to cause this change, which is equal to v minus 0. So we are going to bring this velocity v to 0 in time t. That is nothing but v divided by t is the retardation. So this retardation is going to create some force, and that retardation force is given by mass into retardation. So as we know, force is equal to mass into acceleration. Force is equal to mass into acceleration. So acceleration may be in the increasing rate, then we call it as acceleration, and if it is in reduction form, then we call it as a retardation. So reciprocal of acceleration is retardation. So in the same way, the force of retardation is given by mass into retardation. Mass is given by rho AVL. So as we have obtained, mass of water in the pipe is rho AVL, rho AL into retardation is V divided by T. So this gives us the retardation force. So we call this as equation number 1. Say the force of retardation is obtained if the P is the pressure of intensity or pressure wave which is produced because of sudden closing of wall. So there is a pressure wave developed in the pipe, and that pressure wave which is developed creates the force over the pipe or in the pipe. So therefore the pressure force or force which is created due to sudden closing because of pressure P inside the pipe. P is the intensity of pressure wave. Therefore the force produced is given by pressure into area. So if P is the intensity of pressure, the force due to pressure of wave wave pressure or pressure of wave is given by pressure intensity P into area of pipe. So that is nothing but P into A. Now the force given in equation 1 and this is force in the equation 2, both must be same. The force of retardation and force which is created because of pressure intensity must be same. Therefore equating two forces, that is force of retardation and force due to pressure wave, forces in equation 1 and 2 we get, that is equation 1 is rho AL into V divided by T, which is equal to P into A. So now if we see in this equation, A is there on both sides, so A gets cancelled. So what we get, pressure intensity P is equal to rho L V divided by T. So this is pressure intensity, and we call this as equation number 3. So now as we define pressure head is defined as head H, which is given in meters of water or meters of liquid. H is equal to pressure intensity P divided by rho G. Now we have obtained from this equation number 4, that is pressure intensity P is equal to rho LV divided by T. So substituting this in this equation, so in place of P, that is rho LV divided by rho G into T. So rho gets cancelled. So we are going to get LV divided by GT. LV divided by GT. This is H. So we call this as equation number 4. Say Now if we see here, the wall closure is said to be gradual. Case 1, wall closure is said to be only if time taken t is greater than 2L divided by C. So where L is the length of pipe, T is the time taken, and C is the velocity of pressure wave, where C is the velocity of pressure wave. And this second case, wall closure is said to be sudden. If T is less than 2L divided by C. So this is about the pipe where water hammering process where the closure of wall is gradual. Now second case we see, that is the closure of wall is sudden and the pipe is rigid. Now according to this equation, that is pressure intensity, which we have obtained in previous case, pressure intensity P is equal to rho LV divided by T. So this equation number 3. Pressure intensity P is given by rho LV divided by T. So this was the equation number 3. Just we need it. So the relation between increase of pressure due to hammer in the pipe and time required to close the wave, say here is T is equal to 0. So earlier time was not 0, but in this case time taken to close this wave is 0. So if in this denominator T becomes 0, the pressure intensity P becomes infinity. So as this denominator becomes 0, the pressure intensity becomes infinity, but this is in practice is not going to become infinite. So it is to some extent it is a finite, not a infinite. So from the experiments it is observed that the increase in pressure due to water hammer is finite, it is not infinite, even for rapid closure of wall. So therefore this equation is valid for incompressible fluids when the pipe is rigid. So it is valid for both the cases, that is the fluid is incompressible and when the pipe is rigid. But when a wave of high pressure is created, the liquid gets compressed to some extent. So generally what we assume, that the fluid or liquid which is incompressible, we say that is water or oil. So it also has got certain limit of compressibility, that is also compressible to some extent. So therefore sometimes the material of pipe, even we assume that it is rigid, that also gets stretched and absorbs the shock produced due to sudden closure. So here the shock produced is absorbed by this pipe as well as the wall itself. Now we see L be the length of pipe, whereas V be the velocity of flow in the pipe, A is the cross sectional area of pipe, and K, this is bulk modulus of water. So what we are assuming, that the water or liquid flowing through this pipe is compressible. This is taken with the assumption that the fluid flowing through the pipe is compressible. Then P is the intensity of pressure wave produced and C is the velocity of pressure wave. So what happens here, when valve is closed suddenly, the kinetic energy or velocity is stopped, and that kinetic energy is converted into strain energy of water. So whenever this kinetic energy is stopped or velocity is brought to zero, so this kinetic energy gets converted into strain energy of water. And if the effect of friction is neglected and pipe wall is assumed to be perfectly rigid, there is no expansion, no elongation of pipe is assumed to be a rigid pipe, at that time the kinetic energy gets stored into the liquid flowing through the pipe, which is produced because of water hammering action. So when we stop this flow suddenly, the kinetic energy gets converted into strain energy. So the loss of kinetic energy, how much of kinetic energy is lost? Loss of kinetic energy, we can say, is equal to, generally kinetic energy is half into mass of water, mass of liquid or water, liquid in pipe, into velocity square, v square. So therefore we know half mass of liquid flowing through the pipe is rho al into v square. So this mass is given by rho al. In previous case we have seen this is very first equation. So now rho al into v square. Now gain of strain energy, so whatsoever is this kinetic energy is lost is converted into strain energy. Now we call this as equation number, say, 3, 4. Now it is equation number 5. Equation number 5 gives us the loss of kinetic energy. Now this kinetic energy is converted into strain energy, that is gain in the strain energy, gain of strain energy. Energy of liquid. So where this strain energy is stored? This strain energy is stored in this liquid, and that is given by half P square divided by K, where K is the bulk modulus, into volume of liquid. So this strain energy is stored per unit volume. So this strain energy we can call, or we can equate it 1 by 2 P square divided by K into volume of liquid is A into L, where A is the cross-sectional area and L is the length. We call this as equation number 6. So now what we say, that the energy, kinetic energy which is lost is converted into strain energy. So this complete kinetic energy is converted into strain energy. That is nothing but loss of kinetic energy is equal to the gain of strain energy. Loss of kinetic energy is equal to gain of strain energy. So loss of kinetic energy is given by half rho a l v square is equal to gain of strain energy is half P square divided by K into AL. So now if we see here, AL is there on both sides, we can cancel AL. Half is there on both sides, half we can cancel. So now we can write this as P square is equal to K rho V square, or we can write this as P is equal to V into square root of K rho. Just if we transfer this power on other side, or taking square root on both sides, so on left hand side square root square gets cancelled, where on right hand side we get V into square root of K into rho. So multiplying and dividing this K rho in this bracket, V K rho square divided by rho. So now we can say this as P is equal to. So now this P is equal to, we can write as rho V into C, where C is equal to square root of rho divided by, sorry, K divided by rho. So this K divided by rho is taken as C, square root of K divided by rho is taken as C, and rho square, square root of rho square is taken as a rho outside this bracket. So therefore this equation becomes P is equal to rho V into C for this gradual closure, sorry, sudden closure, considering the pipe to be rigid. So pressure intensity is equal to rho V into C, where C is the velocity of pressure wave produced in the pipe due to sudden closure of a wall. So this is second case. Now coming to the third case, that is sudden closure of wall and assuming that the pipe is flexible. Now here, as we have seen the equation, so before that we discuss about the properties, what we assume. So let E be the modulus of elasticity of pipe. So as we are going to assume that pipe is flexible, there is certainly there will be the chance of scope of elongation in the pipe. Therefore E is taken as modulus of elasticity of the pipe, where 1 by m is the Poisson's ratio of pipe material that you have already studied in strength of material. Then P is the intensity of pressure wave produced in the pipe, and T is the thickness of pipe wall, and D is the diameter of pipe. Now we take this equation, that is equation H is equal to, we have derived L V divided by T, GT. So head pressure, head H in meters of water is given by LV divided by GT. So now we assume that this pipe is not a very thin, it has got thickness T, and the pipe which is subjected to the pressure and which is elastic in nature, having diameter D having diameter D has got the properties as we have seen. Now wave is suddenly developed due to sudden closure of pipe, and that wave is having pressure intensity P. So where the wave which is having pressure intensity P is going to act within the pipe, and because of this action of pressure produced due to sudden closure of wall, so this pipe is subjected to expansion. So due to sudden closure the pressure is developed and this pipe is going to expand, and at the same time this pipe is going to elongate, as this pipe is assumed to be flexible. So here the longitudinal stress is produced when the pipe is elongated, and when this pipe is going to expand, so circumferential stresses are produced. Let us assume that FL be the longitudinal stress produced in pipe. So as sudden wave is produced, so this pipe starts to elongate in the longitudinal direction and produces longitudinal stress. Then let FC be the circumferential stress produced in pipe. Due to sudden pressure developed, the diameter tends to increase, and that is creating circumferential stress in the pipe. Now we see the longitudinal stress FL, which is given by P into D divided by 4 times T. So we have studied thin and thick cylinders. So these equations, thin and thick cylinders, pressure vessels, where we have studied, there we have obtained the equation for longitudinal stress and circumferential stress, that is P into D divided by 2T is the circumferential stress which we have studied in the strength of material. Now the strain energy stored in the pipe material per unit volume is given. So what happens here when this liquid is flowing through this pipe? When it flows through this pipe, this kinetic energy or velocity is brought from V to 0. This kinetic energy is completely destroyed, and that energy is imparted to this material of pipe, and this material of pipe expands in longitudinal direction as well as in circumferential direction. That is nothing but kinetic energy is going to get stored in this pipe material, or this pipe material absorbs this kinetic energy. So this strain energy is absorbed in the pipe material, and this strain energy per unit volume is given by strain energy gain per unit volume volume of pipe material is given by and there is one equation which we have studied in strength of material, that is 1 divided by 2E in bracket FL square plus of FC square minus 2 EFL into FC divided by M, where 1 by M is Poisson's ratio. Now substituting these values of FL and FC in this equation, we get 1 divided by 2E in bracket P D divided by 4T is the value of FL square plus of P D divided by 2T square minus 2 into FL is P D divided by 4T into FC is PD divided by 2T into 1 over M. So assuming that the Poisson's ratio (1 by M) is equal to 1 by 4, we can substitute this 1 by M as 1 by 4. So this becomes 1 divided by 2E in bracket. This we can write as P square D square divided by 16T square plus of P square D square divided by 4T square minus, so P square D square, we can take this as 2 into P square D square divided by 4. 1 by M is taken as 4, so 4 16 into 2, 32 T square in the denominator. So now we can again simplify this. P square D square divided by this is 4T square, okay. 1 divided by 2e. So on simplification, we get this as 1 divided by 2e. So if we simplify this completely, 2 1s are 2, 2 16s are 32. So this term is equal to this first term. So p square d square divided by 16t square plus, and this is minus, gets cancelled. So what is going to remain is 1 by 2e into p square d square divided by 4t square, or this can be written as p square d square divided by 8e t square. So this is the strain energy. We call this as equation, or we'll have this equation further we carry it. So this is the amount of energy stored per unit volume, strain energy stored per unit volume of this material, pipe material. So if we know this complete volume of this pipe material at that time, so total volume of pipe material is given by pi d is the circumference into length L into thickness T. So if we open this pipe, it can be a rectangle of length, width pi d and L length, and having thickness T. So if it has got thickness T, then we can find its volume, that is pi d is width, L is the length, and T is the thickness. So volume of pipe material we can obtain. So total energy stored in the pipe material, absolute energy or total energy, total strain energy, stored in pipe material is given by strain energy per unit volume stored per unit volume into total volume of pipe material. So this is not volume of liquid, it is volume of pipe material. So as we have seen, the strain energy stored per unit volume is given by p square t square divided by 8e t square. Just we have derived this equation. So here this is the equation for energy stored per unit volume of the pipe material into volume is pi t L into T. So now this can be written like this: P square into pi dl. So this d we take small d, diameter of pipe, pi d, p d square. Now we write this as p square pi d square into d into L divided by 8e into T. So this pi is connected with this d square. So here we can rewrite this as p square pi d square divided by 4 p divided by 2 into dl divided by et. So this 8 is splitted into 2 and 4. So now this we can write as p square divided by, so this pi by 4 d square is taken as the area of pipe. So area A into dl divided by 2 et we can write, where pi by 4 d square is taken as the area of pipe. Now loss of kinetic energy of water that we can see here. So we will write this as equation number not written equation number here. Equation number 5, 6. We call this as a 7. This as 7. And this as equation number 8. And then this as equation number 9. Now, loss of kinetic energy of water is given by half mv square. Loss of kinetic energy is given by half mv square, where half mass of water is rho a l into v square. Already this we have derived. So gain in strain energy is also known to us. Gain in strain energy by the water or liquid, by liquid in the pipe, is also known, that is 1 by 2 p square divided by k into volume, which is half p square divided by k into al. So now what we say, the loss of kinetic energy is used by two things. In case when the pipe is rigid, the kinetic energy is completely absorbed by the liquid flowing through the pipe, assuming that the liquid is compressible. Now here the liquid is also assumed to be as a compressible, as well as the pipe material is flexible, that is some sort of kinetic energy lost is absorbed by the pipe material. So the total kinetic energy which is lost by this flowing liquid through the pipe due to sudden closure of wall is splitted into two parts. One is the amount of energy absorbed by liquid, and part of energy is absorbed by the pipe material. Therefore the loss of kinetic energy is equal to the gain of strain energy in water plus strain energy stored in pipe material. Therefore, so loss of kinetic energy is known, that is half rho a l v square, whereas gain in the strain energy of liquid is given by half p square divided by k into al, whereas strain energy stored in this pipe material is given by this equation number 9, that is p square a dl divided by 2 et. So this is p square a dl divided by 2 et. So now half is everywhere, 1 by 2 1 by 2 1 by 2 is everywhere, so this half is cancelled. Now we get this A everywhere, A, A. Then second we have L. L is there everywhere, L is cancelled. So what we get here is rho V square is equal to P square divided by K. P square divided by K plus of P square D divided by ET, or we can call this as rho V square is equal to P square in bracket 1 by K plus of D divided by ET. So now we can call this P square is taken common, so therefore P square is equal to rho V square divided by, this bracket is transferred, that is 1 divided by K plus of D divided by ET in the denominator. Or else P is equal to, we can take square root on both sides. So taking square root, we get V outside this square bracket, and square root of rho divided by, in bracket 1 by K plus of D divided by ET. The square root is applicable to denominator and numerator. So we call this as equation number 10. So this is equation number 10, gives us the pressure intensity in case if the pipe is assumed to be flexible. So here we have completed this water hammering theory as well as derivations. Now as per your syllabus, no numericals are to be dealt in the matter of this water hammer. So we stop here for water hammering, and we will start the new concept in next class. Thank you.